Hello everyone, I'm Sahong, and today I'm going to talk about the bottlenecks in offline RL. In principle, offline RL is great because it can learn a potentially near-optimal policy from a very suboptimal dataset by stitching different trajectories together, unlike behavior cloning or BC. But in reality, it seems like, for example, the recent trend in robotics is just to scaling up behavior cloning with a bunch of data or with scalable architecture, not necessarily using offline RL. And also, if you look at some benchmarks in robotics or offline RL, we often see that the performance of BC is much better than the performance of offline RL, even though it shouldn't be the case. So why is this the case? What's the problem with current offline RL? Well, the main difference between offline RL and behavior cloning is the presence of a Q function or value function. And indeed, many prior methods focus on learning better value functions with better techniques, as you can see here. But actually, is value learning really the main bottleneck in offline RL? Are we actually putting our effort in the right direction to maximally improve the performance of offline RL? To answer this question, in this paper, we analyzed the bottlenecks in offline RL. We first note that there are three potential bottlenecks in offline RL. So the poor performance of offline RL can be attributed to value learning, imperfect value learning, imperfect policy extraction from the learned value function, and imperfect policy generalization to test time states that the agent encountered at test time. And our main hypothesis is that, unlike the prior belief that value learning is the main bottleneck in offline RL, we argue that actually the main bottleneck in offline RL is policy learning, not value learning, so which are both policy extraction and policy generalization. And in the paper we have two analyses, where in the first analysis we compare value learning and policy extraction. And in the second analysis, we analyze policy generalization. So this is our first analysis. Is it the value or the policy? To compare value learning and policy extraction, what we do in the paper is to draw data scaling matrices with different amounts of value data and policy data on diverse tasks. So it looks like this, where we ablate the number of data points or the number of samples for training a value function and also a policy function. And then we measure the performance with all the combinations and then observe how the performance is bottlenecked. For algorithms, we consider three value learning algorithms like IQL, SARSAR, and contrastive RL. And these are all decoupled methods in the sense that in these methods, policy extraction doesn't affect value learning. And we consider three policy extraction algorithms, which are weighted behavior cloning, like AWR, which is behavior cloning but weighted by e to the advantage, and behavior constraint policy gradient like DDPG plus BC, which is just the combination of the Q maximization part and the BC part. And finally, sampling-based action selection like SFBC or IDQL, where we first train a behavior cloning policy, BC policy pi, and then sample n actions from the pi, and then pick the best action with the highest Q value. So these are the methods that we consider, and we test these methods on 8 different environments, including goal condition and pixel-based ones. And this is how the result looks like. So first, this is goal condition estimate large, where we train IQL and AWR, and we draw the data scaling matrix. And this is how it looks like, where we can see that in this specific case, the performance is mainly bottlenecked by the amount of pulse data, so the color gradient is kind of vertical. And then we repeat this procedure with different value learning algorithms like CRL, and different policy extraction algorithms like DDPG plus BC and SFBC. And also, we repeat the entire process with 8 different environments, and please check out the paper for the full results. And here, let me highlight some key observations. Our first observation is that policy extraction is actually much more important than value learning in general in terms of both performance and data scaling. So for example, this is XOR Walker environment, where if you use the AWR policy extraction algorithm, then this is what you get, where we can see that the performances are not very good in general. But if we just switch from AWR to DDPG plus BC, which is another policy extraction algorithm, then we can see that the performance becomes much better, even though they extract policies from the exactly same value function. And finally, SFBC is kind of in between the two. And we found that this is in general the case, meaning that DDPG plus BC is almost always better than the other two, SFBC and AWR. But why is this the case? Why is DDPG plus BC much better than AWR, even though they are kind of in some sense theoretically equivalent? the main difference is in their objectives. So if you look at their objectives, they are actually quite different because AWR has only a single mode covering term, but DDPG plus BC has two mode seeking and mode covering terms. In other words, DDPG plus BC has two modes, but AWR has only one. Actually, this makes a pretty significant empirical difference. So here, what we do is that we ablate the value of the hyperparameter alpha, which kind of interpolates between BC and RL in AWR and DDPG plus BC. So first, this is the results with AWR. So we ablate the value of alpha from 0 to 10, but we can see that when alpha is small, it's obviously like policy bounded because it doesn't use value function at all. But even when alpha is very large, like 10.0, the data scaling matrix is still bounded by pulse data. So the color gradient is kind of always vertical. So AWR is always policy bounded, and this is actually because it has only a single mode covering term. But if you do the same with DDPG plus BC, then when alpha is large, then the performance is kind of policy bottleneck. But when alpha is small, then it becomes value bottleneck, meaning that the color gradient is kind of horizontal. So we can see that DDPG plus BC has two modes. And this is very beneficial because if you look at this case, the in-between case where alpha has the value of 1, then actually we can see that the performance of the entire data scaling matrix is much better than the other two by kind of overlapping these color gradients together. And especially when the data amount is very small, like 0.1 million, it can still a very strong performance that is even compatible with the full dataset case with like 10 million dataset. So that's kind of one reason why DDPG plus BC is better than AWR. And in the paper, we have much more extensive analysis about different pulse expression algorithms. So if you're interested, please check out our paper. Takeaway: do not use AWR, always use DDPG plus BC. Our second analysis is about policy generalization. So this is actually a pretty unique bottleneck in AlphaNRL. So in AlphaNRL, what we do is that we train an agent from a static dataset D, but at evaluation time, we roll out the learned policy in the environment to measure the performance. But at test time, the agent can go outside of the dataset distribution D, and of course, how well it generalizes to such kind of test time states can significantly affect performance. And we are going to analyze this. And to do that, we measure three types of policy accuracy metrics in terms of mean squared error. So these are the metrics that we measure. So they are basically the difference between the learned policy pi and the Oracle optimal policy pi star under three different distributions, which are the training distribution, dtrain, on which the agent is trained, and also the validation distribution, which is a held out set from the training data set, and finally the evaluation distribution. So this is actually just the state marginal distribution of the current policy, and this exactly corresponds to the generalization bottleneck that we are going to measure. And to see how the performance is bottlenecked, we observe how these metrics evolve with additional online interaction data, and how they correlate with the actual performance. And this is the result. So we measure the performance of offline to online RL, where we start online fine-tuning at this red dotted line on 6 different environments. And you can see that just the performance generally goes up because like this is offline to online RL, so it's like what it is. And first we measure training MSE. And actually the result is kind of interesting. So we can see that at the very beginning, the training MSE very quickly drops to a very low value, and then it completely flatlines even with additional online data. The same for evaluation MSE. But if we measure evaluation MSE, then actually we can see that the trend is quite different. And actually the correlation between the performance and evaluation MSE metric is pretty remarkable. So in other words, our observation is that offline to online RL mostly only improves evaluation MSEs, while evaluation and training MSEs are they just remain completely flat. And also, the performance is very strongly correlated with the evaluation MSE metric, not the other two. So what does this mean? Actually, this tells us a very interesting conclusion. So the conclusion here is that maybe current offline RL is already very good at learning the best possible policy if the state is in the dataset distribution. And the performance of OpenRL is often simply bottlenecked by the policy accuracy on novel states that is outside of the data distribution and that the agent encounters at test time. And very few existing methods explicitly address this generalization bottleneck because they mostly focus on pessimism and conservatism, not generalization. But our analysis tells us that it's one of the most important bottlenecks in OpenRL. But what can we do? How can we improve this generalization bottleneck? Is it even possible, given that it may require generalization to a potentially very different distribution? But in the paper, actually, we show that this is actually possible if we do something unusual, which is to further train the policy on novel states at test time. So this is our main idea. So this is what we call test time policy improvement. So basically, what we are going to do is that we further adjust the policy actions based on the learned value function at test time. And our method is actually very simple. It's just a single line method. So this is what we do. We first sample an action from the policy, the learned policy, at test time. And then we just slightly adjust the action in the direction of the Q function by the amount of beta slightly, such that the action can be a little bit better in terms of the value function. Actually, that's all. And this is what we call on-the-fly policy extraction, or OPEX. And in the paper, we show that OPEX and TTT, which is another test time training method, improve performance across 8 different environments. So the takeaway is that test time policy generalization is one of the most important bottlenecks in OpenRL. In summary, we show that current OpenRL methods are often bottlenecked by pulse learning rather than value learning. And here are some open research questions. Is there a better way than DDPT plus VC? How can we train a policy in a way that generalizes very well in test time states? And finally, can we apply these kind of insights into different domains like sequence models or LLMs? So these are pretty interesting research questions, and please check out our paper and blog post for more information, and thank you for listening.